Hello, my fellow cosmic dreamers, and welcome back to Hafee Sleep. Whether you're tuning in from a bustling city where the lights never fade, or a quiet town where the stars still rule the night sky, whether it's the middle of the day for you, or the deep, quiet heart of the night, I'm so incredibly glad you're here. Tonight, we're going on a journey together. A journey to solve the greatest mystery in the cosmos. We're going to talk about the ghost in the machine of the universe, the invisible architect that shapes everything we see, dark matter. But before we dive into the shadows, I have a small request. If the mysteries of the universe captivate you as much as they captivate me, do our channel a huge favor and hit that subscribe button and give this video a wide thumbs up. It truly helps us grow this peaceful community of curious minds. And as we drift through the cosmos together tonight, I'd love to feel connected to you. Drop a comment down below and tell me where in the world you're watching from and what time it is. For you right now, are you cozying down for sleep? Just waking up? On a lunch break? Let's map our little Hafee Sleep community across the globe. Now get comfortable, relax your mind, and let's begin. Imagine you're at a grand, lively party. The music is thumping, the room is packed, and you're watching from the edge of the dance floor. You see a couple over there, spinning and twirling in perfect unison. Their movements are graceful, predictable. You can almost anticipate their next step based on how they're holding each other, the push and pull of their arms. Now imagine you see another dancer, all alone in the middle of the floor, but they're spinning, dipping, and whirling, as if they were in the arms of a powerful expert partner. Their hair flies out, their body leans at impossible angles, yet there's no one there. You wouldn't think, wow, that person is defying the laws of physics. You'd think, there must be someone else there I can't see. Something is making them move like that. Welcome to the grandest party of all, our universe. For the last century, astronomers have been that puzzled observer, watching the cosmic dance of stars and galaxies. They know the music, the fundamental laws of gravity, written by Sir Isaac Newton and later refined by Albert Einstein. They watch the dancers, the stars, the galaxies, the great clusters of galaxies, and they see them moving in ways that, according to all the music sheets we have, should be impossible unless there's a partner we cannot see. A silent, invisible partner that doesn't dance to the tune of light, but most certainly sways to the rhythm of gravity. We call this mysterious partner dark matter. And this is the story of how we came to know it exists, even though we've never seen it, touched it, or truly understood it. Now, to really appreciate this story, we need to understand the music. The music, in this case, is gravity. For a long time, we thought we had gravity all figured out. Sir Isaac Newton gave us the first real set of rules. He said that every object that has mass attracts every other object with mass. The bigger the mass, the stronger the pull. It's a universal force. It's why an apple falls from a tree, why we stick to the earth, and why the earth goes around the sun. It's a fantastically powerful idea that explains so much of our world. It was like learning the basic, beautiful rules of a waltz. But then along came Albert Einstein in the early 20th century, and he showed us that the music was even more complex and wondrous than we'd imagined. He said that gravity isn't just a mysterious force pulling things together across empty space. Instead, he proposed that space and time are woven together into a single fabric, a four-dimensional thing called space-time. And mass, any object with mass, warps this fabric. Imagine a taut rubber sheet. If you put a heavy bowling ball in the middle, it creates a deep well. Now, if you roll a marble near it, the marble will spiral inward, not because a force is magically pulling it, but because it's simply following the curved groove made by the bowling ball. The sun creates a huge well in the space-time fabric, and the planets are just following the curves of that well in their orbits. Einstein's theory of general relativity didn't throw out Newton's ideas. It refined them, gave them a deeper, more profound foundation. It was like we'd been listening to a simple melody, and Einstein revealed it was actually a full, rich symphony with layers of harmony we never knew were there. So, with this magnificent symphony sheet music in hand, the combined laws of Newton and Einstein, astronomers turned their telescopes to the heavens to watch the dance. And for a while, everything seemed to be in order. The planets waltzed around the sun exactly as predicted. Binary stars pirouetted around each other with graceful precision. It seemed the rules were perfect. But when they looked at the largest scales imaginable, at entire galaxies and massive clusters of galaxies, the dance began to look strange. The dancers were moving too fast. They were leaning at impossible angles, performing steps that defied the music they were supposed to be following. It was the persistent, undeniable feeling that there was another dancer on the floor, one you couldn't see, one who was strong and leading the visible dancers in a wilder, faster dance. Our story doesn't start with ultra-modern billion-dollar particle colliders or space telescopes. It begins, as many good stories do, with a meticulous, patient individual who noticed something that just didn't add up. Our hero in this first act is a Swiss-American astronomer named Fritz Zwicky. It was the 1930s, a time of great change in the world and in astronomy. Zwicky was a brilliant, if notoriously abrasive character, known for his sharp tongue and even sharper mind. Now, let's really put ourselves in Fritz Zwicky's shoes for a moment. It's the 1930s. The world is on the brink of monumental change, and astronomy is just beginning to stretch its wings beyond our own Milky Way galaxy. Edwin Hubble had only recently confirmed that those faint, fuzzy spiral nebulae were in fact entire island universes, galaxies far beyond our own. The cosmic perspective was dawning, and the universe had just gotten impossibly, breathtakingly larger. Into this new frontier steps Fritz Zwicky. By all accounts, he was a force of nature. He was brilliant, fiercely original, and had a personality that could charitably be described as abrasive. He didn't suffer fools gladly, and had a nickname for his more cautious colleagues: spherical bastards. Why spherical? Because, he said, they were bastards no matter which way you looked at them. So we're not dealing with a meek, mild-mannered scientist here. We're dealing with a cosmic cowboy, a maverick who was unafraid to venture into uncharted intellectual territory and call things as he saw them. His chosen territory was the Coma Cluster, a sprawling metropolis of galaxies over 300 million light-years away. Today, we have breathtaking images from the Hubble Space Telescope showing it in all its glory, a dizzying collection of over 1,000 galaxies swarming together. But in Zwicky's day, it was a much fainter, fuzzier smudge of light. Measuring it was a monumental task, a testament to his skill and patience. So, he sets out to weigh this city of galaxies. But let's pause and really think about that ambition. How do you weigh something you can't touch, that is almost impossibly distant? You have to be clever. You have to use the universe's own tools. And the best tool we have is gravity. Gravity is the great communicator of mass. It's the force that tells every other object in the universe, I am here, and this is how much stuff I'm made of. Zwicky's approach was a brilliant 1-2 punch. For his first step, the luminous mass calculation, he had to play a sophisticated game of guess the number of stars. He measured the total amount of light coming from the cluster. Now, light is a good proxy for stars, and stars have mass. We have a pretty good understanding of how much mass a typical star has, based on our studies of stars right here in our neighborhood. So, if you know how much light is coming out, and you have a rough idea of how many stars it takes to make that much light, you can make a decent estimate of the total mass of all those stars. It's not perfect. You might miss some dim stars or some diffuse gas, but it gives you a ballpark figure. It's like looking at a brightly lit office tower at night. You can count the windows that are lit up, estimate how many people are in each office, and get a rough idea of how many people are in the building. Then came his second genius step, measuring the gravitational mass. This is where he stopped looking at the light and started listening to the motion. The galaxies in the Coma cluster aren't static. They're all moving, orbiting the cluster's center of gravity. Why? Because gravity is pulling them inward. To avoid simply falling straight into the center and collapsing the whole cluster into a cosmic train wreck, they have to move sideways, fast. The faster they orbit, the more mass there must be inside their orbit pulling them in. This is the same principle that keeps the Earth in orbit around the Sun. The Sun's immense gravity is constantly pulling our planet toward it. But because the Earth is also moving sideways at a tremendous speed, about 30 kilometers per second or 67,000 miles per hour, it constantly misses the Sun. It's forever falling around it. If the Sun were magically more massive, its gravity would be stronger, and to keep from falling in, we'd have to be moving even faster in our orbit. Zwicky realized he could use this cosmic balancing act to his advantage. The orbital speeds of the galaxies would betray the true gravitational weight of the cluster. But how do you measure the speed of a galaxy millions of light years away? You can't pull out a radar gun. This is where the Doppler effect becomes astronomy's superpower. We all know the sound of a passing ambulance, the eeeew as the pitch drops the moment it goes by you. The sound waves are compressed as it moves toward you, higher pitch, and stretched out as it moves away, lower pitch. Light behaves in exactly the same way. When a galaxy is moving toward us, the waves of its light get compressed, shifting its light ever so slightly toward the blue end of the spectrum. When it's moving away, the light waves are stretched, shifting toward the red. By using a spectrograph, an instrument that splits light into a rainbow spectrum, astronomers can look for these tiny shifts. They look for the familiar chemical fingerprints of elements like hydrogen or calcium in the galaxy's light. If those fingerprints are shifted from where they should be, they can calculate the galaxy's velocity with incredible precision. So, Zwicky painstakingly measured these red shifts and blue shifts for galaxies in the Coma cluster. He was expecting to find speeds that made sense given the weight of all the glowing stuff he'd counted. What he found must have made his jaw hit the floor. The galaxies were screaming around at speeds of nearly 1,000 kilometers per second, millions of miles per hour. These were not sedate, stately orbits. This was a frenzied, breakneck dance. When he plugged these incredible speeds into Newton's equations of gravity, the result was a number so huge it defied belief. The cluster had to contain hundreds of times more mass than he could possibly account for with all the stars and gas he could see. Let's go back to our bag of oranges. Zwicky had counted the oranges he could see through the bag. He felt the bag's weight. The weight suggested it was absolutely stuffed, bursting with fruit. but when he looked, he only saw a few. It was as if the bag was mostly filled with something invisible, something that had weight, but that he couldn't see or touch. The galaxies were moving as if they were in the gravitational grip of a monstrous unseen heavyweight. He called this phantom mass Dunkle Materie, dark matter in German language. It was a breathtaking leap, a truly revolutionary idea. But here's the thing about revolutions. They often get a chilly reception. Imagine being Zwicky. You've just made a discovery that suggests 90% of the universe is made of something utterly unknown and invisible. You take this to your fellow scientists. Their reaction? A collective raising of eyebrows. A lot of polite and not so polite skepticism. There were many reasons for this. First, the measurements were hard. The technology of the 1930s was pushing its absolute limits. Could Zwicky be sure about his velocity measurements? Could there be errors? Second, maybe he had underestimated the visible mass. Maybe there was lots of dark gas and dust between the stars, or lots of faint, dim stars he couldn't see that were adding to the weight. These were perfectly reasonable alternative explanations. But the biggest reason his idea was shelved was probably Zwicky himself. His combative personality and his history of proposing wild, sometimes outlandish ideas made it easy for the scientific establishment to dismiss this as another Zwickyism. They thought of it as a curiosity, an anomaly that would probably be explained away by better data someday. They didn't realize that this irritable, brilliant maverick had just stumbled upon the greatest secret in the cosmos. The clue was there, but the world wasn't yet ready to listen. The case of the missing mass was filed away, waiting for another detective to pick it up decades later and realize that Zwicky hadn't been crazy at all. He had been right all along. The story of dark matter might have ended there, a forgotten footnote in astronomy textbooks, if not for a woman named Vera Rubin. In the 1960s and 70s, Rubin, facing immense gender-based barriers in her career, was doing groundbreaking work on the motions of stars within individual galaxies. Our own Milky Way is a spiral galaxy, a vast pinwheel of stars, gas, and dust. We're located in one of its spiral arms. According to Newtonian gravity, stars in a galaxy should orbit the center, much like planets orbit the sun. Now, let's really dive into this pivotal moment in our story, because what Vera Rubin and Kent Ford discovered didn't just add a footnote to astronomy. It rewrote the entire book on what makes up our universe. To truly appreciate the sheer wonder of their finding, we need to put ourselves in their position, to understand what everyone expected to see, and why what they actually saw was so earth-shatteringly bizarre. Picture our solar system again, that beautiful, orderly dance around the sun. It works so perfectly because of a simple, elegant rule. The vast, overwhelming majority of the mass, a whopping 99.8% of it, is concentrated right in the center, in the sun itself. It's the gravitational boss, the star of the show. The planets are just bit-part players orbiting it, because all that pull is coming from one central point. The strength of gravity weakens dramatically as you move away. It weakens with the square of the distance, to be precise. This means if you double your distance from the sun, gravity's pull isn't just halved. It's reduced to a quarter of its original strength. If you triple the distance, it drops to a ninth. This is why Mercury, the innermost planet, has to tear around the sun at a blistering 47 kilometers per second just to keep from being swallowed up. Earth, further out and feeling a weaker tug, can afford a more leisurely 30 kilometers. And poor distant Neptune, feeling only the faintest whisper of the sun's gravity, just putters along at a glacial 5 kilometers. It's a perfect, predictable downhill slope of orbital speeds. For the longest time, astronomers looked at spiral galaxies like our Milky Way and thought, well, that looks like a bigger solar system. You have a bright central bulge packed with stars that seems like the galaxy's sun. And then you have these beautiful sweeping spiral arms where the stars are more spread out. These seem like the galaxy's planets. It was the most natural assumption in the world to think that the same rules must apply. The math was clear. The orbital speed of a star in the galaxy should be determined solely by the amount of mass inside its orbit. A star close to the bright center should feel the pull of almost the entire galaxy's mass and should orbit very fast. But a star way out in the lonely outskirts, in the faint reaches of the spiral arms, it should only feel the pull of the mass inside its orbital path. Since most of the light, and therefore everyone assumed most of the mass, is concentrated in the inner core, a star in the outer regions should be feeling a much weaker gravitational pull. To avoid drifting off into the emptiness of intergalactic space, it should be orbiting much, much slower. This is what every astronomer expected. If you were to draw a graph of this, with the distance from the center on the bottom and the orbital speed on the side, you would get what's called a Keplerian decline, named after Johannes Kepler, who figured out the planetary motions. The line would shoot up very steeply near the center, peak, and then fall off in a long, smooth, downhill slope. It would look like a single, tall, steep mountain. This was the predicted rotation curve. It wasn't just a guess. It was a direct consequence of the well-tested laws of gravity applied to the visible stuff everyone could see. Enter Vera Rubin. Her story is itself a triumph. In an era when women were often actively discouraged from pursuing careers in science, especially astronomy, she persevered with a quiet, relentless brilliance. She wasn't looking to overturn physics. She was just a deeply curious scientist who wanted to map the motions of galaxies in more detail than ever before. She was partnered with an incredible instrument builder, Kent Ford, who had developed a super-sensitive spectrograph. This wasn't just a better telescope, it was a better eye. It could analyze the faint light from the outer regions of galaxies, far from the bright core, with a precision that was previously impossible. They chose beautiful spiral galaxies, similar to our own, and they began their meticulous work. They would point their telescope at a specific point in a galaxy, say, a spot 20,000 light years from the center. They would capture the light from that spot, run it through Ford's spectrograph, and look for the telltale Doppler shift in the light from stars or clouds of hydrogen gas. This would give them the velocity at that precise distance. Then they'd move a bit further out to 40,000 light years and measure again. Then 60,000, then 80,000. They were building a map, point by careful point, of how fast the galaxy was spinning from its center all the way out to its faintest edges. They started plotting their data on a graph, fully expecting to see that familiar mountain shape, the steep rise and the steady Keplerian decline. The first points near the center behaved perfectly. The speeds shot up. Good, they might have thought. Right on track. They kept adding points, moving further out into the spiral arms. This is where the curve should have started its inevitable downhill slide. But it didn't. The line, instead of falling, stubbornly, impossibly, flattened out. They added more points, further out than anyone had ever reliably measured before, in the remote, dark suburbs of the galaxy. The speeds remained high. They did this for another galaxy, and another, and another. The result was always the same. It wasn't a fluke. It was a rule. Stars and gas clouds on the very outermost fringes of these galaxies were hurtling around at the same breakneck speeds as those much closer in. It was, as you said, as if Mercury, Earth, and Neptune were all orbiting at the same insane 47 kilometers. Now just stop and think about the implications of that for a second. Imagine you're on a roller coaster that's whipped around a sharp curve. You're pinned to your seat by centrifugal force, the feeling that you're being thrown outward. The only thing keeping you on the track is the sturdy harness, which provides the centripetal force pulling you inward. Now imagine that same roller coaster car, on the same curve, but moving twice as fast. The feeling of being flung outward would be immense, overwhelming. To keep you on the track at that higher speed, the harness would have to pull you inward with vastly more force. It would have to be made of something unimaginably stronger. This is exactly what was happening to those outer stars. Their tremendous speed meant they were experiencing a phenomenal centrifugal force, trying to fling them out of the galaxy like a stone from a sling. The only thing keeping them in their orbit was gravity's harness, the inward pull of the galaxy's mass. For the harness to be strong enough to hold them at those speeds, there had to be a huge amount of mass generating a huge amount of gravity. But here's the killer point. For a star in the outskirts, the only mass that contributes to pulling it inward is the mass that is closer to the center than it is. The mass outside its orbit pulls in other directions and cancels out. So, if a star 100,000 light-years out is moving just as fast as a star 30,000 light-years out, it means there must be a tremendous amount of mass inside its orbit pulling on it. But when we look inside that orbit, we don't see enough glowing stars and gas to account for that pull. The light, the visible matter, is all concentrated in the inner parts. The only possible conclusion is that the galaxy must be filled with a huge amount of matter that we cannot see. And it can't just be sitting in the center. If it were, it would affect the inner and outer stars the same way the sun's mass affects all the planets. To make the rotation curve flat, this extra mass has to be distributed in a special way. It must form a gigantic, spherical halo that envelops the entire visible galaxy, extending far, far beyond the visible stars. In this halo, the density of this dark matter decreases as you move out, but there's just so much of it that its gravitational influence dominates the outer regions completely. This was Rubin's monumental contribution. Zwicky had found a problem in galaxy clusters, which could maybe, possibly, be explained by some other, more complex phenomenon. But Rubin found the same problem in every single individual galaxy she looked at. Her work was methodical, repeatable, and left no room for doubt. The evidence was no longer a curious anomaly from one grumpy astronomer. It was a clear, universal signal. The universe wasn't just mostly empty space with bright pinpricks of light. It was mostly made of something else entirely, something dark, something mysterious, something that, through its gravity alone, was reaching out its hand and guiding the cosmic dance, making the stars whirl at speeds that should have been impossible. This was the moment the astronomy world could no longer look away. This was the moment dark matter became real. The evidence was now overwhelming, but it was still indirect. It was like investigating a crime scene where you can't find the culprit, but you can see the clear footprints they left behind in the mud. The footprints were gravitational, and soon, more and more pieces of evidence started to pile up, each one adding another detail to the footprint, giving us a better idea of the shape and size of this mysterious entity. One of the most dramatic and visually stunning pieces of evidence came from observing how dark matter can bend light itself. This is a phenomenon predicted by Einstein's theory of general relativity. And if want to grasp the true knowledge of Einstein's theory of general relativity, visit our channel. We have made full-length video slowly explaining the theory of general relativity. Go and check it out if want. Now, we arrive at what might be the most elegant and visually spectacular piece of evidence in our entire dark matter detective story. It's a piece of evidence that doesn't just rely on watching things move, but on watching light itself get twisted and bent by the invisible hand of gravity. To understand it, we have to take a little detour back to our friend Albert Einstein and his grand idea about what gravity really is. You see, for centuries, we thought of gravity the way Isaac Newton did, as a mysterious, invisible force that reaches out across empty space and pulls objects together. The sun pulls on the earth pulls on you. It works, and it's incredibly accurate for most things. But Einstein had a more profound and, frankly, a more beautiful idea. He said that space isn't just a static, empty stage where the cosmic play happens. Instead, space and time are woven together into a single, flexible fabric called space-time. And mass, anything with mass, warps this fabric. Let's use that classic rubber sheet analogy. Imagine space-time is a vast, taut rubber sheet. Now, you place a heavy bowling ball in the center. What happens? It creates a deep, curved dimple. That dimple is gravity. It's the warp in the fabric of space-time. Now, if you roll a marble across this sheet, its path will naturally curve as it enters the dimple. It's not being pulled by a magical force from the bowling ball. It's simply following the curved groove. The marble's path is the straightest possible line it can take on a curved surface. The mass of the bowling ball told space-time how to curve, and the curved space-time told the marble how to move. Now, here's Einstein's brilliant leap. He said that this doesn't just apply to things with mass, like marbles and planets. It applies to everything, including light. Light always travels in a straight line, but what if the very definition of straight changes? What if the space itself is curved? Then light must follow that curvature. Its straight line becomes a curved path. So, if a beam of light from a distant star passes near a massive object like our sun, its path should be bent ever so slightly as it travels through the warped space-time around the sun. This was a stunning prediction. And in 1919, during a total solar eclipse, the British astronomer Arthur Eddington proved Einstein right. He photographed stars whose light was passing very close to the sun. Their positions appeared slightly shifted from where they were supposed to be, because the sun's gravity had bent the starlight on its way to Earth. It was a monumental victory for Einstein's theory, and changed physics forever. This effect, where gravity bends the path of light, is called gravitational lensing. It's called a lens because it acts just like a glass lens, bending and focusing light. Okay, so a big mass can bend light a little bit. Fascinating. But how does this become our most powerful tool for hunting dark matter? Well, scale is everything. Our sun is a pipsqueak when it comes to warping space-time. To get really dramatic lensing effects, you need truly monstrous amounts of mass. You need something like a massive cluster of galaxies. These clusters are the heaviest objects in the universe that are held together by their own gravity. They can contain thousands of galaxies, each with billions of stars, all swimming in a superheated soup of gas that's tens of millions of degrees. The total mass is almost unimaginable. And all that mass creates a truly profound warp in space-time, a deep, deep dimple in our cosmic rubber sheet. Now imagine we're looking at such a cluster with our most powerful telescopes. In the foreground is the cluster itself, a collection of galaxies. But far, far behind this cluster, much deeper in the cosmos, are other, more distant galaxies. The light from these background galaxies is traveling for billions of years to reach us. On its way, it has to pass through the warped space-time around the foreground cluster. And this is where the magic happens. That warp doesn't just bend the light a little, it can bend it a lot. It can act like a crazy funhouse mirror or a giant cosmic magnifying glass. Instead of seeing the background galaxies as neat little pinpricks of light, we see them distorted into incredible shapes. They are stretched and smeared into long, thin, shimmering arcs of light that curl around the cluster. Sometimes the lensing is so perfect that we see multiple images of the same background galaxy, like a cosmic hall of mirrors. It's one of the most breathtaking sights in all of astronomy. But for our detective story, these beautiful arcs are more than just pretty pictures. They are a precise mathematical tool. Light doesn't bend at random. It bends in a very specific way that depends on one thing and one thing only: the amount and distribution of mass in the foreground cluster that is doing the lensing. The more mass, the more the bending. The way the mass is arranged changes the pattern of the distortion. So, by very, very carefully measuring these distortions, the exact shapes, lengths, and positions of these stretched out arcs, astronomers can work backwards. They can run complex computer simulations to figure out exactly how much mass must be in the cluster and exactly where it must be located to create the precise lensing pattern we see. It allows them to create a detailed map of the cluster's total gravitational field. It's a mass map. They are literally using bent light to draw a picture of gravity itself. And this is where dark matter steps into the spotlight, or rather, reveals its shadow in the most dramatic way possible. When astronomers create these mass maps from gravitational lensing and then compare them to maps of the visible matter, the thousands of galaxies, and the hot X-ray glowing gas, they find something astonishingly consistent. The visible matter is not nearly enough to account for the incredible warping of space-time they are observing. The lensing map shows a huge, massive, smooth blob of gravitational force that envelops the entire cluster. The visible galaxies? They are just tiny, bright specks embedded within this vast, invisible halo of mass. It's like looking at a city at night from an airplane. You see the bright pinpricks of light from streetlights and houses, but those lights are all sitting within the massive dark shape of the city itself. The lensing is showing us the dark shape of the city. The glittering galaxies are just the streetlights. The dark matter is the city's land and infrastructure. This was already powerful proof. But then, nature provided us with the perfect experiment, a cosmic collision of unimaginable scale that separated the ingredients of the universe for us, making the invisible visible. This is the story of the bullet cluster. The bullet cluster isn't one cluster, it's two. Actually, it's the aftermath of a high-speed, head-on collision between two galaxy clusters. Think of it as the universe's most epic car crash, happening in extreme slow motion over hundreds of millions of years. It's a gift to science because it let us see how different types of matter behave when they smash together. In any galaxy cluster, there are two main components of visible matter. First, there are the galaxies themselves, those collections of stars, planets, and dust. But surprisingly, the majority of the normal visible matter in a cluster isn't in the galaxies. It's in the form of a superheated thin gas that fills the space between the galaxies. This gas is so hot, it glows not in visible light, but in X-rays. Now let's play out the collision. These two clusters, each with its own set of galaxies and its own cloud of hot gas, come flying toward each other. What happens when they meet? Well, the galaxies themselves are mostly empty space. The chances of two stars actually colliding are astronomically small. So, the galaxies from both clusters largely pass right through each other, like two swarms of bees flying through one another. The hot gas between the galaxies, however, is a different story. This gas is a plasma, a soup of particles. When the two clouds of gas smash into each other, it's like two clouds of smoke colliding. The particles interact, they slam into each other, they create tremendous friction and pressure. They get stuck. They slow down dramatically and pile up right in the middle of the collision. This gas gets squeezed and heated to even more incredible temperatures, making it glow even brighter in X-rays. So, if you point an X-ray telescope like the Chandra Observatory at the bullet cluster, you see a bright, glowing clump of gas right at the center of the collision site. That's the visible matter that got stuck in the cosmic traffic jam. But what about the gravity? Remember, we can map the total mass, the source of the gravity, by using gravitational lensing to see how it bends the light from background galaxies. So, astronomers made a mass map of the bullet cluster, and this is the breathtaking result. The mass map did not show the bulk of the mass sitting in the center with the piled-up gas. Instead, it showed two distinct, large clumps of mass, and these two clumps had sailed right on through the collision site and were now located on either side of the central gas cloud. They had behaved exactly like the galaxies. They had passed right through the entire collision without slowing down, without interacting, without even noticing the other cluster was there. What can possibly explain this? We have the visible gas which got stuck in the middle. We have the total mass from lensing which kept on going. Therefore, the majority of the mass must be something that, like the galaxies, does not interact with itself or with other matter. It is collisionless. It feels gravity, so it got dragged along with the rest of the cluster. But it doesn't feel the electromagnetic force, so there's no friction, no crashing, no slowing down. It just passes through everything. This is a direct, observational picture. The blue clumps on the lensing map, often used to represent the dark matter distribution, are not where the visible matter is. They have been physically separated by the violence of the collision. It is the most compelling visual evidence we have that most of the matter in the universe is not only dark, but it is something fundamentally different from the atoms that make up you, me, the planets, the stars, and the hot gas in clusters. It doesn't do anything except create gravity. It is the universe's silent, ghostly, gravitational architect, and in the bullet cluster, we saw its shadow striding ahead, leaving the visible universe in its wake. It was the moment the invisible partner in our cosmic dance finally left a footprint we could all see. The case for dark matter was now rock solid, but the plot was thickening. We weren't just dealing with a missing component of galaxies. We were dealing with the dominant component of the entire universe. The next major clue came from looking at the very beginning of everything, the Big Bang. So, by the late 20th century, the case was closed. The evidence from spinning galaxies, from colliding clusters, from gravitational lenses, It all pointed irresistibly to the same conclusion. Dark matter was real. It was everywhere. But this revelation only opened up a deeper, more profound mystery. It wasn't just that some galaxies had a bit of hidden mass. We were discovering that the universe we know and love, the universe of stars, planets, and people, is just the glittering frosting on a much, much larger cake. The frosting is what we see, but the cake itself, the bulk of the substance, is something entirely different, something dark and unknown. To truly understand this, we had to stop looking at the universe as it is now, and instead learn how to look back in time, to its very beginning. We had to find its baby picture. And astonishingly, we did. Our story now takes us all the way back to the Big Bang. Now, try to wipe away any idea of an explosion happening in some empty space. The Big Bang wasn't an explosion in space. It was the explosive expansion of space itself. Imagine the entire universe, all of space, time, matter, and energy, compressed into an unthinkably hot, dense, tiny point. Then it began to expand, and it's still expanding today. In the first fleeting moments, the universe was a chaotic, searingly hot soup of pure energy and the most fundamental particles buzzing around at near light speed. It was so dense and so hot that atoms couldn't form. Protons and electrons, which have opposite electrical charges, were ripped apart as soon as they might have tried to join together. And light? Light was trapped. Photons, the particles of light, couldn't travel anywhere. They would zip along for a tiny distance and then immediately smash into a free-flying electron, bouncing off it like a pinball. For 380,000 years, the universe was an opaque, blinding fog. If you could somehow have been there, you wouldn't have been able to see your hand in front of your face, because light couldn't travel in a straight line to reach your eyes. It was like being in the densest, thickest forest fog you can imagine. But the universe was expanding, and as it expanded, it cooled. And cool it did. After about 380,000 years, it had cooled down to a temperature of around 3,000 degrees Celsius. That might still sound hot to us, but in cosmic terms, it was finally cool enough for a monumental change to happen. The free-flying electrons could now be captured by protons. They could slow down just enough to be grabbed by the electrical attraction and form the first atoms, neutral hydrogen atoms. This moment, called recombination, was a cosmic coming of age. It changed everything. Suddenly, the free electrons were gone. They were now locked up in atoms. The fog had lifted. The photons of light, which had been constantly bumping into those electrons, were suddenly set free. For the first time in the history of the universe, light could travel in a straight line, unimpeded, across the cosmos. That first flash of clear light is still traveling today. But the universe has expanded so enormously in the 13.8 billion years since that moment that the light has been stretched. It's been stretched from visible light all the way down to microwave wavelengths, and we can detect it. It's a faint, silent microwave static that comes from every direction in the sky. It's called the cosmic microwave background, or CMB. It is the oldest thing we can ever see. It is the universe's baby picture, taken when it was just 380,000 years old. When this background radiation was first accidentally discovered in 1965 by Penzias and Wilson, it was a smooth hiss. But our technology got better. We sent satellites like COBE, WMAP, and most recently, the Planck mission, to study this baby picture in exquisite detail. And when we did, we found it wasn't perfectly smooth. Not at all. When you look closely, it has tiny variations, tiny ripples in temperature. Some patches are ever so slightly warmer, Some are ever so slightly cooler. We're talking differences of a few hundred thousandths of a degree. But these tiny fluctuations are everything. These ripples are the seeds of all structure in the universe. They are the imprint of sound waves crashing through that early, dense plasma. The slightly denser, warmer spots are where a little more matter had clumped together. The slightly less dense, cooler spots are where there was a little less matter. And gravity is a relentless amplifier. Over billions of years, gravity would have pulled more and more matter into those slightly denser spots. The warm spots in the baby picture are the eventual birthplaces of galaxy clusters, and the cooler spots became the vast cosmic voids. The entire cosmic web of galaxies we see today was written in code in that pattern of ripples. And this pattern is a gold mine. It's like a cosmic barcode. When you scan it, it tells you the exact recipe of the universe, the size of the ripples, how they are spaced, how they are distributed. All of this depends precisely on what the universe is made of. It depends on how much normal matter there is, because normal matter interacts with light and pressure, which affects how the sound waves travel. It depends on how much dark matter there is, because dark matter doesn't interact with light, but it does feel gravity, so it clumps differently and guides the formation of the ripples. It even depends on the shape of the universe itself and the mysterious force we call dark energy. When cosmologists fed the exquisitely detailed map from the Planck satellite into their supercomputers and ran the numbers, the results were as humbling as they were definitive. The universe gave us its recipe card, and it reads like this. All the stuff that makes up you, me, the Earth, the Sun, every star and every galaxy, and all the gas and dust in between, every atom of it, that's what we call normal matter, or baryonic matter. And it accounts for just 4.9% of the total content of the universe. The dark matter, the stuff whose gravitational pull we've been tracing through galaxies and clusters, makes up or 26.8% of the universe. That's over 5 times more than all the normal matter. And the remaining 68.3% is something even more baffling called dark energy. We won't get into that today, but it's the mysterious force causing the expansion of the universe to speed up. Let that sink in. Everything we know, everything we've ever touched, seen, or loved, is made from less than 5% of the universe. We are a rare, beautiful, and exotic impurity in a cosmos dominated by darkness. But the CMB tells us one more crucial thing about dark matter. The pattern of ripples only makes sense if the dark matter is cold. Now, cold here doesn't mean it's icy. In cosmology, cold means that in the early universe, these dark matter particles were moving relatively slowly compared to the speed of light. This is vitally important because it allowed the dark matter to start clumping together very early on. Think of it like this. Normal matter in that early soup was under pressure from all the light photons bouncing off it. This pressure created waves that pushed normal matter around, preventing it from collapsing too easily. It was like trying to clump together feathers in a hurricane. But dark matter is shy. It doesn't interact with light or with normal matter. It only feels gravity. So, while the normal matter was being buffeted by radiation pressure, the dark matter could just quietly, calmly, start to pool together under its own gravity. It formed gravitational wells first. Then, later, when the universe cooled and became transparent, releasing the pressure, the normal matter suddenly found itself surrounded by these pre-existing gravitational pits. It simply fell into them. The dark matter provided the scaffolding, the cosmic framework upon which the visible universe could be built. Without this dark matter scaffolding, the gravitational pull from the paltry amount of normal matter alone would not have been strong enough to form galaxies in the age of the universe. The ripples in the CMB would have faded away without leaving a mark. The universe would be a vast, dark, and boring sea of scattered hydrogen gas. There would be no stars, no planets, no us. So, when we look at that baby picture of the universe, the cosmic microwave background, we are not just looking at a relic of the past. We are looking at the blueprint for our existence. It is the final, undeniable proof that dark matter is not only real, but that it is the master architect of the cosmic structures we call home. It is the silent partner that built the dance floor, long before the stars arrived to dance upon it. So, the evidence is convergent and overwhelming. From the motions of galaxies and clusters, to the rotation of stars within galaxies, to the bending of light, to the cosmic blueprint imprinted in the first light, everything points to the same conclusion. Most of the matter in the universe is dark. It doesn't interact with light. It doesn't form atoms, molecules, planets, or stars. It just is. It exerts gravity and shapes the cosmos on the grandest scales. So here we are. We've followed the clues, we've seen the evidence, and the conclusion is inescapable. The universe is filled with a mysterious, invisible substance that shapes everything we see. We've given it a name, dark matter, but a name is not an explanation. The trillion-dollar question, the great cosmic whodunit, remains. What is it? We know what it's not. This is where the detective work really begins, by eliminating all the usual suspects. The first, most obvious thought is, maybe it's just normal stuff that's hard to see. Maybe it's giant clouds of cold gas, or countless rogue planets and asteroids drifting between the stars, or swarms of black holes. Astronomers call this collectively MACOs, which stands for Massive Compact Halo Objects. It's a great acronym. We've looked for them, and while they do exist, there just aren't nearly enough of them to account for all the dark matter. Furthermore, if there were enough of this normal but dark stuff to make up 27% of the universe, it would leave other telltale signs. It would absorb and block the light from distant objects in specific ways that we simply don't see. So we can confidently rule out the idea that dark matter is just more of the same kind of atoms that we're made of. It's something else entirely. This leads us into the realm of the exotic, the undiscovered. The leading, most popular idea among physicists for decades has been that dark matter is made of a new kind of fundamental particle, one that doesn't participate in the electromagnetic force. This is the key. Normal matter interacts with light. That's why we can see it. But if a particle doesn't feel the electromagnetic force, it is completely blind to light. It doesn't absorb it, reflect it, or emit it. It would be truly, utterly dark. The favorite candidate in this category has been the WIMP. No, not a weak, insignificant person. In particle physics, WIMP stands for Weakly Interacting Massive Particle. Let's break that name down because it's a perfect description. Massive. It has to have mass. We know that because it interacts gravitationally. It has weight. It tugs on galaxies. It's not like a photon of light, which is massless. Particle. It's a fundamental building block of nature, not made of anything smaller. Weakly interacting. This is the most crucial part. It doesn't interact via the strong nuclear force that holds atomic nuclei together, and it doesn't interact via the electromagnetic force, but it might interact via the weak nuclear force. This is the fiendishly short-range force responsible for certain types of radioactive decay. The weak in WIMP is a specific technical term for this force. The beauty of the WIMP hypothesis is that it solves two problems at once. Particle physicists' models of the early universe suggest that the incredibly hot, dense conditions of the Big Bang should have created a whole zoo of particles. Most of them would have quickly annihilated each other, disappearing in flashes of energy. But a certain type of stable, massive particle that interacts only weakly could have survived in just the right abundance to perfectly account for the 27% of the universe we call dark matter. This wonderful coincidence is known as the WIMP miracle, and it made the idea incredibly compelling. So, how do you catch a WIMP? This is where the story gets like a fantastic spy thriller. Imagine you're trying to detect a ghost that can walk through walls. Billions of these ghostly WIMPs are likely streaming through your body, and the Earth, and everything on it, every second. They interact so weakly that they almost always pass through everything without a trace. But almost is the key word. There's a tiny, tiny chance that one of these WIMPs might, on a very rare occasion, bump directly into the nucleus of an atom. Not the electron cloud, but the dense, heavy core of an atom. If it does, it would give the nucleus a minuscule kick, like a pebble striking a bell. Our job is to build the bell and then listen with hypersensitive ears for the faintest possible ring. This is what dozens of experiments around the world are doing right now. They are located a mile or more underground, in old gold mines, tunnels, and caverns. Why so deep? To shield them from the constant rain of cosmic rays, high-energy particles from space that would create a deafening noise and drown out the tiny, quiet ping of a WIMP collision. They use enormous vats of ultra-pure, ultra-cold liquid xenon, or germanium. These elements are chosen because they have large, heavy nuclei, making them bigger targets for a WIMP to hit. The experiments are cooled to extreme temperatures and are incredibly sensitive. They are waiting patiently for that 1 in a trillion event. The problem is, after decades of searching and building ever larger, ever more sensitive detectors, they haven't heard a definitive ping. The eerie silence is starting to make some physicists wonder if the WIMP miracle was just a beautiful dream. This has led the search to broaden. Other candidates are now getting serious attention. One of the most promising is the axion. If a WIMP is a massive, shy particle, an axion is imagined to be an incredibly light and shy particle. It would be billions or even trillions of times lighter than an electron. The axion was actually proposed to solve a completely different, very technical problem in particle physics involving the strong nuclear force. But it turns out it would also have the right properties to be a dark matter candidate. Trillions of them could be flowing through every cubic centimeter of space. And because they are so light and non-interacting, we'd never notice. Experiments to find axions are very different from WIMP detectors. They use powerful magnets inside resonant cavities, trying to convert an axion into a faint microwave photon under very specific conditions. It's a long shot, but so is everything in this business. Then there's a more radical idea. What if we're completely wrong? What if dark matter isn't a particle at all? What if our understanding of gravity itself is flawed? This is the premise of theories like MOND, which stands for Modified Newtonian Dynamics. The idea is that maybe Newton's and Einstein's laws of gravity work perfectly well here in the solar system and on Earth, but they break down on the immense scales of galaxies. Perhaps at these vast distances, gravity behaves differently and becomes stronger, which would explain why stars on the outskirts of galaxies orbit so fast without needing any extra, invisible matter. It's a bold and intriguing idea. The problem is, it has struggled mightily to explain all the evidence. It might be able to explain the rotation curves of some individual galaxies, but it has a very hard time with galaxy clusters, and it completely falls apart when faced with the bullet cluster. Remember, the bullet cluster showed us that the gravity, the mass, and the visible matter have been physically separated. No modification of the law of gravity can easily explain why the gravity would seem to be in a different place than the matter. You need some form of matter that can become separated. Furthermore, the detailed pattern of the cosmic microwave background is a perfect match for a universe that has cold, dark matter in it, and a very poor match for a Mond-like universe. So, the consensus remains. Dark matter is most likely a particle. The hunt continues on multiple fronts. We have the direct detection experiments underground, waiting for a bump in the night. We have particle colliders like the Large Hadron Collider, trying to smash protons together with such immense energy that they might create a dark matter particle, even if we can't see it directly. We would infer its existence from an apparent imbalance of energy and momentum after the collision. And we have indirect detection experiments, telescopes in space and on the ground, scanning the skies for unusual signals, like a faint glow of gamma rays, that could be the signature of dark matter particles, occasionally annihilating each other in the dense cores of galaxies. It is one of the greatest and most profound puzzles in all of science. We are like sailors on a dark ocean. We can feel the waves, we can see the currents, we can map the tides, and we know without a doubt that the ocean is there. We can even chart its depths. But we have yet to catch a single drop of its water to analyze in a lab. We know the dark matter universe is there, all around us, the silent architect of the cosmos. We just haven't learned its language yet. The search for its identity is a thrilling reminder that the universe is far stranger and more wonderful than we ever imagined, and that the greatest discoveries often begin not with an answer, but with a beautiful, compelling, and mysterious question. And so we're left floating here, in a universe where what we see is only a fraction of what truly is. We are surrounded, shaped, and held together by a cosmic secret, a silent, invisible presence that guides the grand dance of the galaxies. I hope this journey into the heart of one of science's greatest mysteries brought a little wonder to your day, or a little peace to your night. If it did, if you enjoy getting lost in the mysteries of the cosmos with us, please consider subscribing to Hafee Sleep. Hit that like button and ring the notification bell so you never miss our next adventure into the unknown. And I'd still love to know, where in the world are you listening from? Drop a comment below and tell me your city and what time it is there. Let's see how far and wide our community of curious dreamers stretches. Thank you so much for watching. Until next time, remember to look up at the stars sometimes and wonder what invisible forces are at work, guiding their light all the way to you. Sweet dreams and good night.